right, everybody, this is 4.2, Graphing Basics. Our last lesson we talked about finding like these key features from a graph. If we had a graph, we could find like the x-intercept, the y-intercept, we could find lots of other stuff. Today we're actually going to get into graphing from an equation. All right, so all of the equations that we're going to have from now on are all going to be in our quadratic equations. Quadratic meaning its highest degree is 2. So if you look at A, B, and C, and any of the other examples as we go along, they're all quadratics. All right, and we talked about it should look like a parabola. So quadratics make a parabola. So let's see if that happens. All right, so one thing that we can do when we graph is we could make a table and find points. So we could do that here for this first one, just so we could have some practice. This is not the easiest way to do it, especially when our equations look like B, where we have like 3 terms and we have to put that all in our calculator and get our answer, and then we have to do it again to find more points, and who knows where the points are good. Maybe they won't even fit on our graph. Maybe they're way too high or way too low. So, but this is a way, and we're going to use this to kind of come up with a pattern that's going to help us graph. Anyways, so if you're trying to find, if we have an x and we want to find a y, what we need to do is we need to substitute it into our equation. So we would end up getting -3 squared. The parentheses is important. So if you're going to use your calculator and you try and square it without, like if you do -3 squared, it's only going to square the 3. It won't square the negative. So it's important to put parentheses, especially when we submit our substitute negative values. All right, so if we put -3, what's -3 squared? Well, that would give you -3 times -3, which is 9. -2 squared, or -2 times -2 is 4. -3 squared is 1, 0, 1, 4, and 9. So we could fill that all in. And what do you notice? Just by looking at our table, maybe that you see that there are repeating numbers and that we have an axis of symmetry. Like the axis of symmetry is right there, where x is equal to 1. And then on the left side, or above it, these values are symmetric to the other side. So we should always see that if we ever want to like make a table. We can plot these as well. So -3, 9 is a little bit out of our graph, but we're going to still plot that. -2, 4, -1, 1, 0, 1, 1, 2, 3, and 3, 9. The last thing we need to do is to connect those dots the best we can. Try and make it look like a parabola. We put arrows on the ends, showing that they keep going forever. All right, and we're good to go. So that is a way, and again, that's fairly easy if it's a nice equation, but look at B at the bottom. It has 3 terms, and it's kind of hairy. So I already have this filled in, but we're just going to go and do one of them together. So if we wanted to do this by hand, we would plug that in for every time we have an x. So we would do -1 squared minus 4 times -1 plus 3. We'd need to plug that all into our calculator, including its parentheses, and we would evaluate that, and we would end up getting 8. So there's one of our points, and that would take you a while. We kind of talked a little bit on how to maybe save some time when we're doing this. If you have any questions on that, let me know. All right, so I'm just going to have these filled in so that we can look at those, just to save some time, but it might be good for you to give those a try, plug those in. All right, and as you look, all of them, they go down to a point, and then they start going back the same way. Same for C, it goes down, goes back up. Okay, so it's symmetric, it has an axis of symmetry. Okay, but what we really want to see is what happens if we find the rate of change. Now, rate of change is basically the slope between 2 points. So the change in x is always going to be 1. So we're just going to kind of set that on the side, and we're going to only look at like the difference of the y's. So to find the rate of change, we're going to do our second number minus our first. So 4 minus 9, that would give us negative 5. And we can keep going, and we'd end up getting negative 3, negative 1, 1 minus 0 is 1, 2, or 4 minus 1 is 3, 9 minus 4 is 5. So it looks like we have some sort of pattern. We can kind of see that as we look at this graph. Here we go down 5. It's kind of like our slope. Down 5 over 1, down 3 over 1, down 1 over 1. And then we start going up. So over 1, up 1, over 1, up 3, over 1, up 5. So we can kind of see that pattern on that graph. And what we want to see is what happens if we find the rate of change for B and C. So if you want to, pause and give that a try. Do the same sort of thing, like 3 minus 8. That gives you negative 5. And just go along and see what you get. So if you did go and do that, you would end up getting this. And for C, we would get the same. Oops, minus 1, 1, 3, and 5. So the rate of change for all of these are exactly the same. If we were to plot these other ones, so like for B it was negative 1, 8, which is right here, and then we have 0, 3, which is right here, and then we have another one at 1, 0, and then it keeps going, fill in all those other ones. So if we connect those dots, so here's our B example, okay, B. All right, you still see, if you start at the vertex, it has the same slope. We still go over 1, up 1, over 1, up 3, over 1, up 5. So it seems like there's this pattern, and that will make it be super nice as we go along. We could do the same thing for C. 2, 11's not there, but we could do 3 and 6. And then what was next? 4 and 3. And then I think that's what our parabola would look like. So as you look, all of those parabolas are exactly the same. They have the exact same rate of change. It's just kind of shifted around the graph, okay? So it looks like they all have the same rate of change, and that's what we're asking here, is what do you notice about the rate of change? It's the same. So from that vertex, we just do 1, 3, 5. We go over 1, up 1, over 1, up 3, over 1, up 5. All right, let's see what happens for these others. I already have those written down just to save some time, but what do you notice about its rate of change? Is it the same as what we did above? It's not. Above it was like we had 1, 3, 5, kind of that was our pattern. Here it's 2, 6, 10. So what we noticed in class is it looks like it's been doubled. Like it was 1, 3, 5, and now it's twice as big. It's 3, 6, 10. And we talked about why is that? Where on the equation could we possibly see what's making that difference? And we looked at the first 3 problems, and we noticed that the coefficient for all of them, the leading coefficient was 1. And then for these 2, the leading coefficient was 2. And for F, the leading coefficient is 3. So for all of the cases, it's all based off of 1, 3, 5. But if A is 2, we double it. If A is 3, we triple it. So instead of doing 1, 3, 5, we're going to do 3, 9, 15. Okay? And then this would still go the opposite direction too. Our slope there is 0, or negative, sorry. If A, our leading coefficient, was 4, then we would do 1 times 4, 3 times 4, which is 12, and 5 times 4, which would give us 20. So we'd do 4, 12, and 20. So it doesn't matter what, I mean, even if we have A's that are crazy, then we can always still kind of come up with that same pattern. All right? All of these examples, A was positive. We're going to see what happens if we have like -1 was A, or -2 or -3. We'll see what happens there. So basically, the A determines the rate of change. Okay? All right, so let's kind of put this together. In order to graph a parabola, we need to first find our vertex, because that's the point where we start doing our growth pattern, 1, 1, 3, 5. Okay? And then we'll use our growth pattern. Again, the growth pattern of a quadratic, we always go over 1, and then we're going to go up or down 1 times A, whatever A is. So in this example, we went over 1, and then we went up 1. Over 1, up 3. Over 1, up 5. Okay? Again, if A was not 1, then we would go over 1, up 1A, over 1, up 3A, over 1, 5A. And when I say 5A or 3A, we're just saying 5 times what A is, our leading coefficient. So let's just talk about some problems together, and hopefully that will help. So first we need to plot our vertex. For this homework, I'm giving you the vertex. In the future, you're going to need to find the vertex from the equation, and there's different ways to be able to come up with that. So for now, we're just going to plot 2, -4. Okay? And then we need to figure out what the growth pattern is. Again, it depends on A. So we need to figure out what A is. A is what's in front of x squared. So here, A is 1. If we look at B, A is -2. If we look at C, A is 3. And here, A is -1. So again, it's just the leading coefficient, what's in front. B and C are kind of in a different form. Usually you've only seen standard form, which is like A and D. But either way, just what's in the very front. If we have parentheses in our equations, it's always going to be what's in front of your parentheses. Okay? So like C and D, or C and B, they were both in front of those parentheses. All right, so we found our A's. Now we need to find our growth pattern. Well, that's just 1A, 3A, 5A. And in this situation, A is 1. So 1 times 1 is 1, 3 times 1 is 3, and 5 times 1 is 5. So all the time we go over 1, and then we're going to do what the growth pattern says. So we're going to go up 1 because it's positive. So we go over 1, up 1, over 1, up 3, over 1, up 5. And we'll do it on the other side too. Okay. The marching band is on the back, or out there. I don't know if you can hear the beating of the drums. Anyways, okay, so here's another example. We have -1, 8. There's our vertex. Always start by plotting our vertex, and then we'll use our growth pattern. So this time, 1A, 3A, 5A. So A is -2, so whenever we plug that in, we're going to multiply those numbers by -2. So -2, 3 times -2 is -6, and 5 times -2 is -10. So we go over 1, and now we're going to go down 2, because it's -2. Over 1, down 6, and then over 1, down 10, which is outside of our graph, so we don't need to plot it. And then we do it on the opposite side because we know that parabolas are symmetric. We connect the dots the best that we can, and we're done. Okay? Sorry. C. Again, we have our A already, and we're going to do 1A, 3A, 5A, and 1 times 3 is 3, 3 times 3 is 9, and 5 times 3 is 15. So we're just evaluating when a is 3. We plot it 5, comma, negative 3, which is right here. And we use our growth pattern. So over 1, up 3 this time, over 1, up 9. And we'll do it on the other side as well. So you should always at least have 5 points when you graph, if you want full points. And you need to clearly show where the points are. Okay? I know some of you might just use your vertex and then kind of just do the rest of the parabola just freehand, but you got to have the points on there if you want points. Huh, just get how I said that? All right, next, last one, we have 4, comma 4. And now a is negative 1. So we have 1a, 3a, 5a, and a is negative 1. So we plug that in, get negative 1, negative 3, and negative 5. So we'll go over 1, over 1, down 3, over 1, down 5 on both sides. And we're done. Okay. We also had these on the side to have some practice. You'll have that on the homework too. So this stuff here was from 4.1. And if you want, I'll go over this in case you'd like some extra work. Examples, I'll do that real quick. So here we go. And I'm missing 2 things here. We're missing positive, negative, and end behavior. Okay, so x-intercepts, again, that's where it crosses the x-axis, so that's negative 3, comma 0 and 1, comma 0. So that's those. Y-intercept is where it crosses the y-axis, so that's 0, comma 6. Axis of symmetry is the line that cuts the parabola in half, and to make a vertical line, you've got to do x equals, and here it's negative 1. Do we have a max or a min? Well, here we have our max right here, a value of 8. That's how high it goes. Again, why we don't do a minimum is because these arrows keep going forever, which means that it never reaches a minimum. Okay. Domain is always negative infinity to infinity. Basically, as the parabola keeps going, as those arrows keep going, it keeps getting further and further away from that axis of symmetry, and it never stops. Okay? And then range is all possible y values. So you start at the lowest, so those arrows keep going all the way to negative infinity, and then we scan to the top. How high it goes would be 8. And we do a bracket because we include that value. That is how high it gets. Increasing, again, this is kind of tricky this is probably the most tricky thing, is increasing is where it's getting higher and higher. So it keeps getting higher and higher until it reaches that axis of symmetry. So it goes from negative infinity to negative 1. Okay? And basically the axis of symmetry separates the increasing part from the decreasing part. So what we use for that increasing is always going to be our x value. It's also the number from the axis of symmetry. Decreasing would be the opposite side of that, so that would go from negative 1 to infinity. Direction of opening here is down. This example was up for A. Positive, so we're going to try and find where we have positive values. Positive y values, I should say. So we have positive values, I'll do that, is right between those 2 points. Everything between negative 4 and 1, all of the y values are positive. They're all above the x-axis. So we'd have positive goes from negative 3 to 1. And then negative values are everything else. So we have 2 parts, the left part and the right part. So the left part goes from negative infinity to negative 3. and then it also has 1 to infinity. So if we combine those three together, we should have the whole domain. Same thing with increasing and decreasing. If we combine those together, we should have the whole domain. All right, end behavior is basically saying where are those arrows headed? So as we mentioned before, those arrows keep going away from that axis of symmetry in the x direction. So as x goes to positive infinity, what's happening to the y's? So this arrow keeps going down and down and down towards negative infinity. And as we go the opposite direction, as x goes to negative infinity, so as we go this way, as we go, I guess maybe I shouldn't do that, maybe we're getting away this way, our x values go that direction, our y values are going that direction. So as x goes to negative infinity, y goes to negative infinity. So for this example, for A, the y's are going to positive infinity, both of them. All right, both of the arrows. All right, so that's about it. If you have any questions, please let me know. I'd love to help you. See ya.